My previous video I called improved low ohms measurement. Well, this one is improved low ohms measurement. And what I was doing in the last one was I had this LM317 adjustable voltage regulator with some resistors set up to make a constant current source of 331.4 milliamps, which I could then pass through an unknown very low ohms resistor, measure the voltage across it, and divide by that 0.3314 amps, and then I'd know how many ohms this was. And I've improved a little bit. Here's the circuit I have there. 4 15 ohm resistors made 3.75 ohms, and that programs the LM317 to produce 331.4 milliamps. And I pass that through this thing, which is 19.985 ohms, and measured the voltage across that so I could verify that the current was, that's how I calculated the current. There was 6.624 volts across it, divided by that resistance gives that current. So I knew what current was going through the resistance under test, and then you just divide whatever voltage you measure across it by that current, and that tells you how many ohms there is. So I've made an improvement. I've integrated this resistor onto there and reduced the current from 330 odd down to precisely, or very close to, 100 milliamps, because that way it's much easier to do the calculations. Dividing by 0.1 is very easy, you just multiply by 10. So here we go. This is what we've got, 12.5 ohms in the programming resistor now, and that sets the current to 100 milliamps. And we have a 10 ohm resistor instead of this 20 ohm one. Measure the voltage across that, and we know the current. And in fact, these are both adjustable. So first I adjust this to be exactly 10 ohms, and then with current running through it, adjust this one so that we get exactly 1 volt across that resistor there. And a 10 ohm resistor with 1 volt across it means there's 100 milliamps running through it, and therefore 100 milliamps running through the resistor under test. So, and the implementation I've got here is this, 4 56 ohm resistors in parallel, and then in parallel with that 150 ohms, actually 120, it should be 150, but I made a mistake and it's got 120 in there, but no big deal, and 100 ohms trim pot. And on the 10 ohm side, 247 ohms, 239 ohms all in parallel, then in parallel with that 120 ohms in series with the trim pot. So with no power, just nothing connected here, we adjust this to get 10 ohms there, then we turn on the power and make a connection here. We've got the constant current running, and we adjust this so that we get 1 volt across there. I did this a few days ago. Let's see if it's drifted since I last adjusted it. Yeah, I think I've fiddled with this one, which is there, but let's see how close this one is still to 10 ohms. That's this resistor here. So put it all on a nice little perf board and hot snotted it onto the heatsink and wired everything up pretty nicely, and it's here. These are just 1% resistors, half watt. We'll measure this 10 ohm resistor and see how close it is. For 10 ohms, to get any sort of accuracy, of course, you've got to use Kelvin connection. So we'll go to 4-wire mode on there and put this guy. So let's just tune it up and increase the resolution here. And just adjust this to try and make it exactly 10. I've calculated these resistors so that the this trim resistor gives us plus or minus 1.5% adjustment, and I think that's pretty wide. I'm going to make another version where it's much tighter, because this, moving that last digit only takes a smidge of a turn, even though these are 20 turn or 25 turn trim pots. I also don't like these connections. Yeah, I don't like these connections, the way I've got them set up. My next version I'll have proper banana sockets for force and cent connections. I don't know why it's bouncing around so much. Let's try more power line cycles. Yeah, that's pretty good. That's very close to 10.40. Let's call that calibrated. And now connect it all up and pass some current through it and check the voltage across that for 1 volt and adjust this to get exactly 1 volt. Okay, got the battery set up. Power positive goes into the input of the regulator and the output we just short to negative, and those two wires are measuring the voltage across this second resistor, the 10 ohms. So plug in some, turn that to volts, and plug the battery in. Okay, now it's almost a volt, bit low, so we'll adjust the, now we're adjusting this resistor until we get 1 volt across that one. Then we know we've got 100 milliamps running. So pretty close, but again this is very fiddly because it's set so that these trim resistors are plus and minus 1.5% of the total, and that's a bit wide. So you do need a decent multimeter to be calibrating something like this, but if you're mucking around with milliohms, you probably already have, or you should have, a decent meter, you know, at least 4.5 digit meter. I'm having trouble with this because it's 6.5 and I'm trying to get those last 2 digits sorted. If I only had 4.5 digits, I'd think it was spot on. Yeah, very pretty. I'm going to call that pretty good. Pretty close to 1 volt there. Okay, let's try doing some actual measurements. I'll put that 1 volt into the top one just so we can monitor it. So the top one is measuring that 1 volt through there, and we'll measure the voltage across our unknown resistance with the bottom meter and pass some current through it with this. So for instance, this here is a 1 milliohm resistor, 100 amps, 100 millivolts, 1 milliohm. So, and the trouble with using meters like this, even though it's a good meter, it's only passing a sense current of 1 milliamp. So 1 milliohm with 1 milliamp running through it develops a voltage across it of only 1 microamp. So you know, that's getting right down in the noise. And then for this guy, which is a fifth of that, 200.2 milliohms, we're trying to measure 200 nanovolts. So even though we've gone down to from 300 to 100, that's still 100 times the current that the meter uses normally. So an improvement. We'll stick this through that guy and measure the sense terminals, and we should get 1 millivolt. 1 millivolt? 0.1 millivolt, yes. So we have to multiply everything we read by 10 because it's a tenth of an amp. We've got to multiply it by 10 as if it was 1 amp. So that would be very close to 1 milliohm. Let's try the big brute. 0.2 milliohms. And we can tell and still got 1 volt up there, very nice. If I store 0.1 in the Y register of this thing and then put it in maths function, 0.2 milliohms. So now it's reading ohms directly, or sorry, yeah, ohms directly. 0.2 by 10 to the minus 3 is 2 milliohms. Very close. Still a bit all over the place, but then what do you expect of this? Just a bloody voltage regulator and a few resistors. It's pretty damn good. Try this one again. 1 milliohm, 1 by 10 to the minus 3. And we can measure higher resistances too, like this one should come out at 19.985. 19.98. So with 16 volts coming in, we could probably measure up to about a few hundred ohms. You could go down to even 5 volts coming in. You'd be able to still measure up to what, 50 ohms. But we don't use it. It's not for measuring those sort of ohms. It's for measuring very low ohms. And this is what I set out to measure right in the beginning. This should be 11.6 milliohms. So 11.6 milliohms. Anyway, so there you go. It's a bit better than the previous one, so it's an improved. But I want to improve it a little bit more with this time using 0.1% resistors. So 3 decimal places, or 3 significant digits on the numbers. I haven't ordered them yet, but 0.1% resistors. And this is calculated so that the resistor, the variable resistor, only trims plus or minus 0.1% of 10 ohms or 12.5. And that should give a lot more movement for even the last digit on those meters there. That could go in, I'm thinking just stick it in a little box like these things. Pretty cute and cheap. Or one of these. Yeah, I don't know, we'll bother making a video when I've done that, but that'll be my poor man's milliohm meter current source. So all you need is that, which is pretty cheap. I also had a couple of capacitors for stability and a diode for input protection against reverse polarity. More banana sockets, so you put your resistor under test here, but you've also got force and sense sockets for measuring the resistance of this guy to get that to 10 ohms, and then you just short these two and use 2 of these to measure the 1 volt to adjust this guy. I just sort of give you that quick update. Hope you enjoyed it. Please like and catch you later.